Hello everyone. In today's section, we are going to understand minimize large object allocation can be a best practice. We all think that we are not forced to do anything for the garbage collection. So, how we will handle the space complexity of our application. So, these things we are going to cover in today's video. So how to minimize the large object collection? So we all aware about there are in when we execute our application, there are two types of uh, uh, memories are there, right? Stack and heap, correct? So let's understand one uh, snippet or one this particular section, which is based on a garbage collection from the ASP.NET documentation. So when you go ahead here in a garbage collection, okay, which is under the memory management. So where you can observe there is one section, the large object heap. So the .NET garbage collector divides the object up to into the small and large objects. So when the large objects, some of its attributes become more significant than if the object is small. For instance, compacting it, that is copying it into the memory elsewhere on the heap, can be expensive. So because of this, the garbage collector places the large object on the large object heap. So basically, as you can see in this particular diagram, there is a stack and there is a heap. So again, the heap again divided into two parts, okay? Small and large objects, okay? Why? Because consider to we want to make a space and moving the large object to the another location for the sequential or compaction of a memory, it will be little bit expensive. So again, heap is divided into for the small and large object allocation. So this article from this ASP.NET documentation will discuss what qualifies an object as a large object and how the large objects are allocated, collected, and what kind of a performance implications the large object impose. So how a large object ends up on a LOH, large object heap. So consider what is the criteria for the large object. So if the object is greater than or equal to the 85,000 bytes in a size, it's considered as a large object. So this number was determined by the performance tuning. And when the object allocations require for or more than 85,000 bytes, the runtime allocates it into the large object heap. So let's see what we have here. So normally, normal data types are stored in the stack and the objects stored in a heap. Again, heap is divided into the small object and large object heap. If your object is more greater than 85 KB, then it will shift it to the large object heap. Now, heap is divided into two parts. Small objects will be covered under the or stored under the small object heap, like the object A, B, C. And if the object is large, like kind of a list or huge amount of data which we have fetched from the API or a database, such kinds of objects are stored on the large object heap. Now, if you see that the objects are not stored sequentially, they're stored anywhere. So, to making the space, we just ASP.NET just implement this particular technique. So, now what exactly the Gen 0, Gen 1, Gen 2 kind of a garbage collector? Now what happened, how the garbage get collected, how the memory will get deallocated, all these things we understand again. Now the garbage collector is a generational character. It has a three generations, okay? Generation 0, Generation 1 and Generation 2. The reason for having the three generation is that the well-tuned app, most objects die in a Gen 1, Gen 0. For example, in a server app, the allocations associated with each request should die after the request finished. It means once we have given the response, the gen 0 or kind of a allocations will deallocated and it gets finished. In a flight allocation request will make it into the gen 1. They dies there. Essentially, Gen 1 acts a buffer between the young object areas and long-lived object areas. So it's kind of a buffer between. So consider Gen 0 requires more space than more functionality than Gen 2 and Gen 1, like kind of a things. It's a kind of a buffer. So newly allocated objects from new generation of objects and are impact implicitly generation 0 will collect most of the object will get collected by the generation 0 collections. However, if they are the large object, they go on a large object heap. So if your object is greater than certain amount, then um, more than 85,000, then it will transfer to your large object heap, which is sometimes referred to the generation 3. Generation 3 is a physical generation that is logically collected as a part of a generation 2. It's now the large object belongs to the generation 2 because they are collected only during the generation 2 collections. When a generation is collected, all its younger generation are also collected. So for example, when generation 1 happens, both the generation 1 and 0 as well as at that time, both the generation will get collected. And when the generation 2 happens, the whole heap is collected. For this reason, generation 2 is also called as a full GC. Okay, full heap get collected and the memory will get deallocated, the space will get created. So this article refers to the generation 2 GC2 instead of a full GC. Okay, so generation 2 garbage collection is also called as a full GC, but for this particular article, they are considering full GC as a generation. Okay, because we have to understand, we want to understand the generations. So generations provided a logical view of a GC heap. Physically, objects lived in a managed heap segments and blah 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 blah. You can read from here. Let's go ahead with the generation heap. So when the garbage collection is triggered, the GC traces through the leave object and it will compact it. But because compaction is expensive, the GC sweeps the LOH. It makes free list out of the dead objects that can be reused later to satisfy the large object collection request. So adjacent dead objects are made into the one free object. Now, reallocation is a little bit difficult. Okay, so when garbage collection happen, large object transfer or reallocation will be difficult. So it is a little bit heavy for the garbage collection to compact these kinds of a large object allocation. So now .NET may decide to compact the LOH automatically. This means that if you are allocating the large objects and want to make sure that they don't move, you should still pin them. Okay, so if you are considering we want to compact the space, we don't have a inner space. So, but we can't move these kinds of a huge amount of objects. So now how we can resolve these things? The first generation GC will where object 1 and object 3 are dead and it forms generation 2 after the first generation. GC where object 2 and object 5 are dead. Note that these are following figures are only for the illustration purpose. They contain very few objects to better show what happens on the heap. Okay, so we are considering this image. Now see, GC0, what we have, it starts 0, 1, 2, 3. Okay, after GC0 generation, GC 1 and 3 get transferred and 0 and 1 get collected. Okay, now if you can observe here, so figure 2 shows that after generation 2 GC, that shows the object 1 and object 2 are dead and GC forms the continuous free space out of the memory. These are the small objects, it get collected and free memory will get allocated. Okay. Now, to occupy by the object 1 and object 2, which then was used to satisfy the allocation for the request of a object 4. The space for the last object, object 3, to end the segment can also be used to satisfy the allocation. Now what happened? These two objects deleted in a generation 2. Now we have a in between space uh, between object 0 and object 3. So in this space, we are allocating the another object. Okay, and till we have this particular space. Now, this space will get wasted if we are not able to fit any kind of object which require that much of space. So if there isn't enough space to accommodate the large object allocation request, what GC will do? GC first attempt to acquire more segments for the OS. If that fails, it triggers the generation 2 in the heap for freeing some space. Now it is difficult. Okay, object 3 is a large object. Now we don't have a space. GC2 will ask more space from the OS. And it is a little bit difficult. I hope you understood. Okay, let's summarize the things. Okay, so GC1, GC0 will short-lived, it is medium-lived, and it is long-lived. So consider short-lived and medium-lived object releases the space, and now we have enough space, but that much space is not sufficient for sequential data allocation. Okay, so at that time, that memory space will get wasted, and we can't move the objects from GC generation 2 because they are long-lived and they are a large object. So in this case, we are wasting the memory. To reduce it, what we have to do? We have to minimize the large object allocation. Try to maintain the object. Okay, and how we are going to do it? So this is the one example. Okay, how we minimize it. Consider we are copying the huge amount of photos from one place to another place. We are copying, reading, and writing the things. Okay. Now what we have used in this example, read all bytes kind of a method is there. File dot read all bytes. Okay. And we are calling it, what is the method name here? Copy file async. Okay. Now instead of copy file async, we are using stream copy file async. Okay. Then what will happen? So first check the performance. Okay, now another method is stream copy file async. Okay, here is we are using the buffer, and by means of it, we are just creating a file and we are using the file stream, and by means of a file stream, we are just reading and writing the things. Now these are two examples. First one, normal read all bytes async, and second one is file stream, and we are writing it by means of file stream. Now, by using the profiler, we are just checking the performance of these two things. Okay. Now, you can see here in this, just a minute, let me slide show and present a view, and I just open the ledger to point out the things. So here you can see in the example one, okay, GC count is maximum 24 and we are using this much. But in a second example, we are not allocating, or GC2 is not get used. Okay. In the first example, GC count used and it's near about 24. And here you can see LOH, large object heap, how much it get used and how many times GC will get called. GC2, generation 2 garbage collection get called here 26, and here you can see 0. Okay. Now, this is the way we can just use objects, okay, minimize the large object allocation to reduce the functionality, okay, to reduce the allocations, or to reduce the space complexity, okay. Now let's summarize. To avoid or minimize the allocations on a large object heap in ASP.NET, what we can do? Use the object pooling and array pooling to reuse the objects and arrays. Segment large arrays or objects into smaller pieces. Utilize span and memory for slicing and avoiding the unnecessary copying. Be mindful of string concatenation by use the string builder and use appropriate stream classes. Okay. Prefer value types to avoid the heap allocations. Minimize boxing and large object serialization. Okay, so wherever it's not needed, don't use it. Precise collections and defer initialization of a large object when necessary. So these strategies will help and reduce the large object heap pressure and improve the garbage collection performance and make you the ASP.NET application more efficient. Okay. Now, if you observe these things now, so you will say, okay, what is the use of these things? Our applications are working fine. Why we have to do these things? So when you are checking the performance on a higher level after deploying, and if you have a larger amount of clients and users to your product, then at that time you will understand the importance of these things. But you can't modify your application at that time. So take care of these things before you develop, okay, before you start building your application. So it is important, but it is we normally neglect these things, performance issues and performance things. We just only check the out, but we will never check or review the code and check the performance of and how our code is optimizing. These small things, no, minimizing large scale objects and defining the standards, and then and identifying the hot code paths, and then understand the blocking codes. Okay, so these are the prevention criteria. Okay, we don't want to reach at that point where our application will collapse. So these things we have to take care and we have to measure while we are developing our application. So it is important. Okay, so let's go ahead. I think we skip one thing. Caching, I will repeat. I hope that we have covered in the previous block, but still, we will cover that in this section also, caching. But before that, let's go ahead with the avoid blocking calls. So avoid blocking calls is indeed a best practice, especially for the web application that need to handle the multiple concurrent requests efficiently. So why it is important? Okay, avoid blocking calls. Okay, we are calling multiple time a single object or shared object. Okay, so how to avoid and why it is important? So improves the scalability, asynchronous programming. Obviously, we are accessing common function, common block of code or common data by two flows, then obviously it will a deadlock condition, right? And how we do it, why it is important. To improve the scalability, asynchronous programming allows the server to handle more concurrent requests with fewer threads. So when a thread is waiting for IO or any kind of a API or HTTP request or a database, it can be used to process other requests. So something is blocking, then we have to do the background test. Okay, consider this particular block of uh, data is allocated or some thread is using, then we have to do the background task, asynchronous task. Better to resource utilization, responsiveness, performance, preventing thread pool starvation. So because of these reasons, what we need to do, we need to avoid blocking calls. So how we resolve it? Use asynchronous programming, leverage asynchronous APIs, avoid blocking calls in a controller, and configure asynchronous middlewares. Okay. So find out where these kind of a calls are happening, and to resolve these kinds of a calls, what we need to do, we need to use the asynchronous programming wherever some shared data is accessed by multiple threads. We can go ahead with the asynchronous programming or asynchronous API, or try to avoid it itself inside the controller. Make a controller action async to prevent the blocking. The ASP.NET thread pool. Use async versions of common methods like task.delay instead of threads.sleep. Next, Configure asynchronous middleware. So consider middleware is accessing some common features or common data, then at that time you can make it asynchronous middleware. Ensure that your ASP.NET Core pipeline uses asynchronous middleware components. So these are the few things. Okay. If you want more details about how to avoid blocking calls, we have to check. Okay. All these best practices are based on a condition. It's not, I'm not forcing you to follow each and everything. Just check your criteria, project requirement. Based on that, utilize most of them. Okay. I hope that it is clear to you all. Let's stop this particular video and see you in the next video. Take care. Bye bye.